Tonight, while cities sleep beneath glowing streetlights and oceans move quietly against distant shores, the universe is expanding. Not just stars, not just galaxies, space itself. At this exact moment, every galaxy beyond our local cosmic neighborhood is drifting farther away from every other galaxy, carried outward by the stretching fabric of space-time itself. The universe is not sitting still like a frozen stage where matter simply moves around inside it. The stage itself is growing larger every second, and it has been happening for 13.8 billion years. The strange part is that you cannot feel it. Your body is not expanding. The Earth is not being pulled apart. The solar system remains bound together by gravity, stable and silent beneath the larger motion of the cosmos. Yet beyond the scale of galaxies, reality itself is unfolding in every direction like an endless fabric being stretched by invisible hands. For centuries, humanity believed the universe was eternal and unchanging. The stars appeared fixed. The heavens looked permanent. Ancient civilizations imagined the cosmos as something divine and motionless, a perfect structure suspended forever above human life. Even M. Any early scientist believed the universe existed in a stable state that had no true beginning and would never truly end. Then physics shattered that illusion. In 1915, Albert Einstein published the general theory of relativity, one of the most important scientific achievements in human history. His equations revealed something extraordinary. Space and time were not separate things. Together, they formed space-time, a flexible cosmic fabric that could bend, stretch, and warp under the influence of matter and energy. Gravity was no longer a mysterious force acting invisibly across empty space. Gravity became geometry. Mass curved space-time itself, and objects simply followed those curves. But hidden inside Einstein's equations was a disturbing implication. The universe could not remain static forever. The mathematics insisted that space-time itself had to either expand or contract. Einstein disliked this conclusion. At the time, the accepted belief was that the universe was eternal and unchanging. So Einstein inserted an extra mathematical term into his equation, something he called the cosmological constant, represented by the Greek letter lambda. Its purpose was simple. E dot counteract gravity and hold the universe still. For a while it worked. Then the universe proved him wrong. In 1929, astronomer Edwin Hubble made a discovery that permanently changed humanity's understanding of existence. By studying distant galaxies, he found that nearly all of them were moving away from us. Even more shocking, the farther away a galaxy was, the faster it appeared to recede. The universe was expanding. Space itself was growing larger over time. Einstein reportedly called the cosmological constant his greatest blunder, believing he had artificially prevented his equations from predicting the expansion correctly. For decades afterward, scientists assumed the story was mostly understood. The universe had begun in the Big Bang and had been expanding ever since. The only remaining question was how expansion would end. Most physicists believed gravity would slowly pull everything back together. Since gravity attracts matter, the expansion of the universe should gradually slow over billions of years, like a ball thrown upward, eventually losing speed before falling back down. That assumption survived for most of the 20th century. Then came 1998. 2-1. Independent research teams, one led by Saul Perlmutter and another by Brian Schmidt, were studying extremely distant exploding stars called Type 1a supernova. These explosions are important because they shine with nearly identical intrinsic brightness, making them reliable standard candles for measuring enormous cosmic distances. The scientists expected to confirm that cosmic expansion was slowing down. Instead, they discovered the opposite. The supernova appeared dimmer than expected, meaning they were farther away than existing models predicted. The only explanation was astonishing. The universe was not slowing. It was accelerating. Something unknown was overpowering gravity itself and forcing the cosmos outward faster and faster with every passing second. The discovery shocked the scientific world. For months, researchers assumed they had made mistakes in their calculations. Instruments were checked. Data was reanalyzed. The possibility of experimental error was examined again and again. But the conclusion remained unavoidable. An invisible force was driving the expansion of the universe. That force became known as dark energy. Today, scientists estimate that ARK energy makes up nearly 68% of the total energy content of the universe. Ordinary matter, every star, every planet, every human being, every atom in your body makes up less than 5%. The rest is something we cannot see, cannot touch, and still cannot fully explain. And hidden inside that mystery is a terrifying question. If dark energy is what keeps the universe expanding, what happens if it suddenly stops? Dark energy may be the most important thing in the universe, and yet nobody has ever seen it. No telescope has photographed it. No laboratory has captured it inside a machine. It leaves no visible trail across the sky. It does not glow, reflect light, or interact with matter in any way we can directly observe. But despite being invisible, it controls the fate of the cosmos. To understand why, you first have to understand something deeply unsettling about reality itself. Empty space is not actually empty. Right now, the space around you feels silent and motionless. The air in your room seems calm. The desk beneath your hand feels solid and permanent. But physics tells a completely different story. At the atomic level, matter is almost entirely emptiness, the atom. S inside your body are made of tiny nuclei surrounded by clouds of electrons separated by enormous distances relative to their size. If an atom were expanded to the size of a cathedral, the nucleus would be smaller than a grain of sand sitting at its center. Everything else would be empty space. And even that empty space is alive with activity. Quantum physics reveals that the vacuum of space is constantly fluctuating. Tiny particles appear and disappear in fractions of a second, emerging from the quantum fields that fill all reality before vanishing again almost instantly. These are called virtual particles, and although they cannot be directly observed in the ordinary sense, their effects are measurable. The vacuum is not nothingness. It is a restless ocean beneath existence itself. Somewhere inside that invisible ocean hides dark energy. Scientists believe dark energy may be a property of space-time itself, an intrinsic energy woven directly into the vacuum of the universe. Unlike ordinary matter or radiation, dark energy behaves in a way that seems to violate human intuition. Normally, when something expands, it becomes weaker. If you spray perfume into a room, the scent spreads out and becomes faint. If gas expands inside a container, its pressure drops. Energy usually dilutes as volume increases. Dark energy does not. As the universe expands, the density of dark energy remains nearly constant. This changes everything. Because if the amount of dark energy per unit of space stays the same while space itself continues growing, then the total amount of dark energy in the universe actually increases over time. In other words, every new region of space arrives carrying more dark energy with it. The universe expands, and expansion creates more of the force causing expansion. It is a feedback loop built into reality itself. Physicists describe this behavior using something called the equation of state parameter, represented by the letter W. If W equals exactly -1, dark energy behaves as a cosmological constant, a permanent property of empty space that never changes. This is currently the simplest explanation consistent with observations. But if W is even slightly different from -1, the consequences become terrifying. If dark energy weakens over time, gravity may eventually overpower it. Expansion would slow, halt, and reverse. Galaxies would begin falling back toward one another in a collapsing universe, ending in a big crunch. If dark energy grows stronger instead, the opposite happens. The expansion accelerates without limit. At first, galaxy clusters drift apart faster and faster. Then galaxies themselves become isolated. Eventually, even gravity inside solar systems fails. Planets drift away from stars. Stars lose their hold on matter. Finally, the expansion becomes so violent that molecules, atoms, and even atomic nuclei are torn apart. This scenario is called the Big Rip. Reality itself is shredded by expansion. And yet the strangest part is that physicists still do not understand what dark energy actually is. When scientists attempt to calculate the energy of empty space using quantum field theory, the most successful framework in modern physics, the predicted value is catastrophically wrong. Not by a little, not by a factor of 10. The prediction differs from the observed value by roughly 10 to the 120, a number so absurdly enormous that many physicists call it the worst prediction in the history of science. Somehow, the equations describing quantum fields produce a vacuum energy vastly larger than time, the dark energy we actually observe in the universe. This mismatch is known as the cosmological constant problem, and it remains one of the deepest unsolved mysteries in physics, which means humanity has arrived at an extraordinary moment in scientific history. We know dark energy exists because we can see its effect across the cosmos. We know it dominates the universe. We know it controls the ultimate fate of space-time itself. And yet we do not know what it is. Not really. The greatest force shaping the destiny of reality is something modern science still cannot fully explain. And hidden inside that uncertainty is a terrifying possibility. If dark energy is woven into the vacuum of space itself, then the stability of the universe may depend entirely on a property of reality we barely understand at all. If the expansion of the universe stopped tonight, you would not feel it. There would be no earthquake beneath your feet, no sudden darkness swallowing the sky, no violent shockwave racing across Earth. Cities would continue glowing beneath the night. Airplanes would cross oceans. Children would sleep peacefully in their homes, unaware that reality itself had just changed. Forever. And that is what makes the idea so terrifying. The greatest event in cosmic history could begin in complete silence. At this moment, the expansion of the universe has almost no effect on human life. Gravity easily overpowers cosmic expansion on local scales. The Earth remains bound to the Sun. The Moon remains bound to Earth. The Milky Way itself holds together despite the stretching of space-time occurring across the larger universe. But beyond galaxies, in the enormous emptiness between clusters of matter, space is constantly expanding. The distances between galaxies increase not because galaxies are flying through space like bullets, but because space-time itself is stretching beneath them. Now imagine that process suddenly stops. The outward growth of the universe freezes. For the first time in 13.8 billion years, space-time no longer expands. At first, almost nothing changes. Distant galaxies continue moving away because they already possess momentum from billions of years of cosmic motion. Telescopes still observe redshifted light crossing the darkness. The stars above Earth appear exactly as they did the night before. But underneath that apparent calm, gravity. IT quietly begins reclaiming the universe. Without expansion pushing galaxies apart, there is no longer a force resisting the collective pull of matter. Every galaxy cluster, every filament of dark matter, every massive structure in the cosmos begins exerting its influence more strongly. The expansion had acted like tension pulling the cosmic web outward. Now, the tension is gone, and gravity never sleeps. The first measurable changes would appear in the cosmic microwave background radiation, the faint afterglow left behind by the Big Bang itself. For billions of years, this radiation has cooled as the universe expanded, its wavelengths stretched longer and weaker by the growth of space-time. But once expansion stops, the cooling ends. The temperature of the universe freezes in place. And if contraction begins even slightly, the process reverses. The cosmic microwave background starts heating again. At first, the increase is tiny, detectable only by extremely sensitive instruments. But over millions and billions of years, the heating becomes impossible to ignore. The universe slowly transforms from a cold, expanding cosmos into a warmer and denser one. Galaxy clusters begin, in drifting inward. Immense cosmic filaments stretching across hundreds of millions of light years tighten like threads being pulled together. Regions once separated by impossible distances slowly collapse toward one another under gravity's patient pull. The night sky changes. Distant galaxies that had once vanished beyond the cosmic horizon begin returning into view. The observable universe grows brighter and more crowded. Over unimaginable spans of time, more and more of the cosmos becomes visible as light from ancient regions finally reaches us. For a brief era, the universe becomes more connected than ever before. But that beauty hides catastrophe. As galaxies collide more frequently, massive waves of star formation ignite across the cosmos. New stars are born in violent bursts as gas clouds crash together. Supernova explosions become increasingly common. Radiation floods intergalactic space. The universe grows brighter, hotter, more hostile. Eventually, the background temperature of space rises so high that stars themselves begin to fail. A star shines because it is hotter than the surrounding vacuum, allowing heat and radiation to flow outward into colder space. But now space is no longer cold. The universe itself becomes hotter than the stars. At that moment, the direction of energy flow reverses. Stars stop cooling. Instead, they absorb heat from the collapsing cosmos around them. Their outer layers swell and destabilize. Entire stellar systems become trapped inside an increasingly violent radiation bath spreading across all existence. Planets are stripped bare. Atmospheres evaporate. Oceans boil into steam. The chemistry required for life begins to collapse. As temperatures continue rising, atoms themselves cannot survive. Electrons are torn away from nuclei, transforming matter into plasma. Molecules disintegrate. Biological structures vanish. Everything the universe spent billions of years building begins unraveling in reverse. The cosmos returns to the state from which it was born, a furnace of radiation and collapsing matter. And then comes the final stage. As contraction accelerates, the density of the universe rises toward unimaginable extremes. Galaxies disappear into merged superstructures. Black holes consume entire regions of space. Matter compresses beyond anything modern physics can fully describe. In the last moments of a collapsing universe, even atomic nuclei may fail. Protons and neutrons are crushed together under temperatures and pressures greater than those inside the cores of stars. And finally, spacetime itself collapses toward a singularity, a point where distance loses meaning, where time breaks apart, where every law of physics humanity has ever discovered reaches its limit and simply stops. Beyond that boundary, science has no answer. The equations fail. The universe becomes unknowable. And somewhere inside that final collapse lies one of the most haunting truths in modern cosmology. Everything humanity has ever loved, built, remembered, or imagined exists only because the universe expanded long enough to allow it. There is a possibility hidden inside modern physics so disturbing that many scientists hesitate before describing it out loud, not because it is impossible, but because it might already be waiting somewhere in the universe right now. It is called vacuum decay. To understand it, you must first understand something terrifying about reality itself. The universe may not be stable. Everything around you, stars, planets, galaxies, atoms, even the laws of physics governing them depends on the vacuum of space remaining exactly as it is. We tend to think of empty space as nothingness, a silent emptiness between objects. But quantum physics reveals that the vacuum is actually a physical state with its own energy, structure, and properties. And according to some theories, the vacuum our universe currently occupies may only be temporary. Physicists call this a false vacuum. Imagine a ball resting inside a shallow valley high on a mountainside. The ball appears stable. It can remain motionless there for an incredibly long time, but somewhere below lies a deeper valley, a lower energy state where the ball truly belongs. If the ball is disturbed strongly enough, it falls. And once it falls, it never returns. Vacuum decay proposes that reality itself may exist in that shallow valley. The laws of physics we know: gravity, electromagnetism, nuclear forces, atomic stability may only work because the vacuum of the universe currently occupies this metastable state. But somewhere beneath it could exist a deeper, more stable vacuum with entirely different physical laws. If a transition to that lower energy state ever occurred, the con. Sequences would be unimaginable. A tiny bubble of true vacuum would form somewhere in spacetime, perhaps triggered by an extreme quantum fluctuation, perhaps by conditions inside black holes, perhaps by a catastrophic change in dark energy itself. No one knows. But once the bubble formed, it would expand outward at the speed of light. Nothing could stop it. Not stars, not galaxies, not matter itself. Inside the bubble, The constants of nature would change instantly. The mass of the electron could become different. The electromagnetic force might weaken or strengthen. The strong nuclear force holding atomic nuclei together could fail completely. Chemistry, as we understand it, would collapse in an instant. Atoms might no longer exist. Matter could lose its structure entirely. The universe inside the bubble would obey completely different rules. And because the bubble wall travels at light speed, no warning would ever be possible. You would never see it approaching across the sky. There would be no final broadcast from astronomers, no sirens, no countdown. The moment the bubble reached Earth, every particle inside your body would be rewritten according to the new L. W's of physics before your brain could process a single thought. One moment, reality exists. The next moment, reality becomes something else. This is not science fiction invented for dramatic effect. Vacuum decay emerges naturally from quantum field theory, the same framework that accurately predicts the behavior of particles with astonishing precision. And the idea became even more unsettling after the discovery of the Higgs boson at CERN in 2012. The Higgs field gives fundamental particles their mass, and the exact mass of the Higgs boson suggests something extraordinary. Our universe may sit dangerously close to the boundary between stability and instability. Not definitely doomed, but not guaranteed safe either. Some calculations suggest the vacuum could remain stable for periods vastly longer than the current age of the universe, trillions upon trillions of years. Others imply that under the right conditions, decay could theoretically happen at any moment. No one knows which possibility is correct. That uncertainty alone is enough to unsettle physicists, because it means reality itself may be balanced on an invisible edge. And dark energy only deepens the mystery. If dark energy is truly tied to the vacuum of space-time, then any sudden change in cosmic expansion could potentially disturb the vacuum state itself. The halt of expansion would not merely alter the motion of galaxies, it could change the fundamental energy structure of reality. The universe would not simply collapse physically, it could collapse conceptually. The laws governing existence might dissolve along with space-time itself. And yet the most haunting aspect of vacuum decay is not its violence, it is its silence. Human beings instinctively imagine catastrophe as loud and dramatic explosions, fire, collapsing cities. But vacuum decay would arrive without emotion, without intention, without warning. The universe would not attack us. Reality would simply transition into a different state, indifferent to every form of life inside it. Civilizations would vanish without history. Stars would disappear without ashes. Entire galaxies would be erased before light itself could carry news of their destruction elsewhere. The cosmos would continue, but it would no longer be our cosmos. And perhaps that is the most terrifying idea modern physics has ever produced. The end. D of the universe may not come from destruction. It may come from reality quietly deciding to become something else. After all the equations, all the collapsing galaxies, all the terrifying possibilities hidden inside dark energy and vacuum decay, one question remains suspended over everything. Why does the universe allow consciousness to exist at all? For most of human history, we believed we stood apart from the cosmos. Ancient civilizations looked at the stars and imagined the universe as a stage built for human life, a vast heavenly machine turning silently around us. Even after science displaced Earth from the center of existence, people still imagine themselves as observers standing outside reality, studying it from a safe distance. But modern cosmology has destroyed that illusion. We are not outside the universe observing it. We are inside it, made from it. Every atom in the human body was forged in ancient stars that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was created inside collapsing stellar furnaces long before Earth existed. Human life is not separate from cosmic history. It is one, small continuation of it, and none of it would have been possible without expansion. If the universe had remained compressed after the Big Bang, matter would have stayed trapped inside a superheated plasma where atoms could never form. If gravity had overwhelmed expansion too early, stars would never have survived long enough to forge heavy elements. Chemistry would have remained simple. Planets would never have formed. Biology would never have emerged. No oceans, no forests, no civilizations, no minds capable of wondering why the universe exists. Everything required time. Time for stars to live and die. Time for galaxies to evolve. Time for planets to cool. Time for evolution to slowly transform chemistry into awareness. The expanding universe created those conditions. It stretched space-time enough for temperatures to fall, for matter to organize itself into increasingly complex structures, for chaos to slowly become consciousness, which leads to one of the strangest ideas in philosophy and physics. The universe may only be observable because it expanded in a way that allowed observers to exist. This idea is connected to the anthropic principle, the observation that human beings can only find themselves in a universe compatible with conscious life. If the laws of physics had been even slightly different, if gravity were stronger, if dark energy were larger, if expansion had ended too soon, life may never have appeared at all. A universe without observers would remain silent forever. No one would witness its stars. No one would ask questions about its origin. No one would know it existed. And yet somehow, against impossible odds, the cosmos produced minds capable of studying the very universe that created them. That realization changes the meaning of consciousness itself. Perhaps awareness is not an accident sitting pointlessly inside the universe. Perhaps awareness is what the universe becomes after billions of years of evolution, a way for reality to look back at itself. Human beings are collections of atoms that learn to think. Neurons exchanging electrical signals inside the brain somehow generate memory, imagination, fear, love, mathematics, music, and curiosity. The same laws of physics governing galaxies also govern the chemistry inside human thought. The universe created stars. Stars created elements. Elements created life. Life created consciousness. And consciousness turned its eyes back toward the sky and asked, what is happening to the universe? That question may be the most extraordinary event in cosmic history, because for billions of years, the universe expanded in silence. Galaxies formed and drifted through darkness without meaning or observation. That eventually, on at least one small planet orbiting one ordinary star, matter became self-aware. The universe gained the ability to know itself, and that makes the question of cosmic expansion feel strangely personal. If expansion is what allowed awareness to emerge, then what happens if expansion stops? Not merely to galaxies or stars, but to meaning itself. What happens to consciousness in a universe collapsing back into darkness? What happens to memory, art, love, curiosity, and every human story ever told when space-time itself begins to die? Physics cannot answer that question completely. No equation can measure what awareness ultimately is. Science can describe particles, energy, gravity, and quantum fields. But it still cannot fully explain why the universe contains subjective experience at all, why matter is capable of becoming conscious. And perhaps that mystery is more profound than dark energy itself. Because in the end, the strangest fact about the universe is not that it expands, not that galaxies collide, not that reality may someday collapse or decay. The strangest fact is that a universe born from chaos produced beings capable of feeling wonder about it. For 13.8 billion years, space-time expanded, cooled, and evolved until atoms learned to ask questions, until the cosmos became aware of its own existence, until reality looked into the darkness and through us finally asked what it was becoming. And maybe that is why the silence at the center of modern physics feels so powerful. Because when we ask what happens if the universe stops expanding, we are really asking something far deeper. What happens when the universe can no longer dream about itself?